Every time you look at something, you destroy every other version of it that could have existed. That sounds like philosophy. It's physics. And by the end of this, you'll understand why a tabletop experiment from the early 1800s still keeps physicists awake at night. Because what it reveals about reality is something most of us were never taught to accept. In 1803, Thomas Young set up one of the simplest experiments in the history of science. He took a beam of light and aimed it at a barrier with two thin slits cut into it. Behind the barrier, a screen. If light were made of tiny particles, like little bullets, you'd expect to see two bright bands on the screen, one behind each slit. Simple. That's what should have happened. Instead, the screen lit up with a whole series of alternating bright and dark bands. An interference pattern. The kind of pattern you see when two sets of ripples overlap in a pond. Light was behaving like a wave, passing through both slits simultaneously, interfering with itself on the other side. For a century, that was the story. Light is a wave. Case closed. Then quantum mechanics arrived and tore the case back open. By the early 1900s, physicists discovered they could dial down the intensity of the beam until they were firing individual particles, single photons, one at a time. One photon, one tiny packet of energy, fired at two slits. It can only go through one slit, right? It's a single particle. Pick a door. The photon hits the screen. A single dot appears. Then another. Slowly, dot by dot, the pattern builds. And after thousands of individual photons have made their solitary journeys, the screen shows that same interference pattern. Bright bands, dark bands, ripples overlapping, as if each single photon passed through both slits at the same time and interfered with itself. One particle, two paths, simultaneously. Sit with that for a second. A single photon, a discrete unit of matter and energy, appears to travel through two separate openings at once. The only explanation that fits the math is that the photon exists in a superposition of states. It takes both paths. It occupies multiple possibilities until it reaches the screen and becomes a single dot. The possibilities collapse into one outcome at the moment of detection. Strange enough, but the real crisis came when physicists asked the obvious next question. What if we watch which slit the photon goes through? They placed detectors at the slits, tiny instruments designed to register which opening each photon actually passed through. And the moment they turned those detectors on, the interference pattern vanished, gone, completely. The screen now showed exactly what you'd expect from tiny bullets. Two bands, one behind each slit. The photons behaved like particles, taking one path, making one choice. The wave behavior disappeared the instant someone gathered information about the path. Turn the detectors off, the interference pattern comes back. Turn them on, particles, off, waves, on, particles. Every single time. So what changed between those two setups? The photons were identical. The slits were identical, the screen was identical. The only difference was whether information about the photon's path was being recorded. The act of measurement, of acquiring knowledge about which slit, forced the photon to commit to a single reality. This isn't a metaphor about perception shaping experience. The physical outcome changes based on whether information is extracted from the system. The pattern on the screen is measurably, photographically different. The universe at the quantum level seems to hold multiple possibilities open until an observation pins one of them down. Physicists tried everything to find a loophole. Maybe the detectors were physically bumping the photons, disturbing their trajectories with some mechanical interaction. So they made the detectors gentler, more subtle. They used schemes where the detection method couldn't possibly push the photon. The result held. Any method capable of determining which slit the photon traversed, no matter how delicate, killed the interference pattern. The critical variable was information every time. Then came the experiment that should have been impossible. In 1999, physicists performed what's called a delayed choice quantum eraser experiment. The setup is devilish. Photons are fired through the double slit, and after passing through, each photon is split into two entangled partners. One partner heads to the main screen. The other heads to a separate detection system that can either preserve or erase the which path information. The key, the choice to preserve or erase that information, happens after the first photon has already hit the main screen, after the photon has already landed. Its dot is already recorded, and yet, when the data is sorted later, the photons whose partners had their path information erased show an interference pattern. The ones whose partners retained path information show the particle pattern. The decision made after arrival somehow corresponds to the behavior displayed before it. The photon's past seems to depend on a future measurement, as if the universe retroactively decides what the photon did based on what information will eventually be available about it. This is where most people's intuition starts to buckle. We live in a world where the past is fixed and the future is open. The delayed choice experiment suggests that at the quantum level, that assumption cracks. The photon's history, wave or particle, both slits or one, appears to remain undetermined until the entire informational picture is complete, even if that picture completes after the event already happened. Several interpretations try to make sense of this. The Copenhagen interpretation says the wave function, the mathematical description of all possibilities, collapses upon measurement. Before observation, the photon genuinely has no definite path. The question, which slit did it go through, has no answer until you create the conditions for an answer to exist. You're asking about a property that the universe generates on demand. The many worlds interpretation offers a different frame. Every possible outcome occurs. The photon goes through both slits in every case. Measurement splits the observer into branches. One branch sees left slit, another sees right slit. The interference pattern disappears because the branches decohere from each other. You only experience one branch, so you see one result, but the wave never actually collapses. Everything happens, you just lose access to the other versions. Both interpretations agree on the operational fact. The measurement changes the outcome. They disagree on what changes means. Copenhagen says possibilities become real. Many worlds says possibilities become separated. Either way, the observer's interaction with the system determines which reality that observer experiences. And this extends beyond photons. The experiment has been replicated with electrons, atoms, and even molecules containing hundreds of atoms. In 2019, researchers demonstrated quantum interference with molecules of over 2,000 atoms, objects large enough to have a chemical formula that takes a full line to write out. Even these behave like waves when unobserved and particles when measured. So where does quantum end and classical begin? Where does the superposition stop? Your desk, your coffee cup, your hand, these are all made of quantum particles that individually obey these rules. The reason you don't see your coffee mug in two places at once is decoherence. Large objects interact with so many environmental particles, air molecules, photons, thermal radiation, that they're being measured by their environment trillions of times per second. The superposition collapses almost instantly. The environment itself acts as an observer, constantly forcing matter to choose, which means the classical world you inhabit, solid, singular, definite, is what happens when observation is everywhere. Your everyday reality is the product of continuous, relentless measurement by everything around you. The quantum weirdness is still there, underneath. We just live in a world that's too noisy to let it show. You've been collapsing wave functions since the moment you were born. Every photon that hits your retina forces a quantum event to commit. Every surface you touch pins down positions that were fractions of a second earlier, smeared across probabilities. Your senses are measurement devices, and the world assembles itself in response. The double-slit experiment strips away the noise and reveals the machinery underneath a single particle, two slits, and a question that still has no comfortable answer. Does reality exist before you look? The math suggests something closer to this. Reality exists as a field of possibilities, and observation is the process by which one possibility becomes actual. The photon doesn't decide. You do. Or more precisely, the interaction between you and the photon is where the decision lives. The particle and the observer are one system. Separating them is the illusion, and the strangest part might be the simplest. This experiment requires no billion-dollar collider, no satellite array, two slits, and a light source. The most disturbing fact about the universe is reproducible on a kitchen table, and the only thing it requires from you is the willingness to look.